defined as. So here, the average of z squared over the circular cylinder, x squared plus y squared equal to r squared for 0 less than L. This is the open cylinder we talked about in example 4, right? As I say, assume the caps are open. So what's the area of the curved side? Yeah, 2 pi RL, right? So does that make sense? Like the circumference times the height is the surface area. Of course, you could just integrate the ds for the cylinder I've erased at this point, but you could do that. So that's the total surface area, and then I'm calculating the integral of z squared ds, but well, we worked this out. It was r d theta dz. So we had to integrate that. Theta goes full sweep. Z goes from 0 to L because of the problem statement. And lo and behold, we've got this divided by that, and we find that the average happens to be L squared over 3. So we can calculate the average of a function over a surface. We simply calculate the surface area integral, and we divide by the surface area. We can also calculate centroids of surfaces. Like here's a calculation of the centroid of a cone. So here I've got the cone with angle phi naught, it's pi over 4, right? And so I'm supposing that it has uniform density. So the center of mass calculation with uniform density we call the centroid, right? So to do that, I just calculate basically the average of x, y, and z over the cone, and that's how you do it. Now, of course, here I personally don't know the area of a cone right off the top of my head, so I got to work that out. So since ds in the particular pi over 4 angle is rho over root 2 d theta d rho, I just have to integrate that from what to what, from like 0 to 2 pi and 0 to r. So when I do that, that gives me like r squared over 2, I think, and a 2 pi. So I get, looks like pi r squared over root 2. Yeah, pi r squared over root 2 is the area. And then, of course, I have to work out those. Now, of course, if you think about the cone, it's geometrically evident that the average x and the average y is 0, right? Because it's symmetric about x and y. But the z is the more interesting part. So the average z is given by this calculation right here. Notice that we're just doing nothing more than using the ds formula we found for the cone today, integrating it against a function. So there's that. You can also calculate the moment of inertia, which is the rotational, in some sense, the rotational mass, if you will. And to do that, you integrate the distance from the rotation axis times dm, which here about the z-axis, r is the distance from the z-axis. So this is, this is calculating the moment of inertia about the z-axis. I have to integrate r squared like that. Now here, r squared, remember the relation for between r and rho for spherical and cylindrical coordinates is that r is equal to rho sine phi. So that means that r is equal to rho divided by the square root of 2 here, which is why I've replaced my r squared with a rho squared over the square root of 2 squared, also known as 2. And so that's that. Now here's one. Scalar surface integral of the function xyz on the graph z equals x6 plus x plus y, and between y equals 0 and y equals x squared going from 0 to 1, this is a kind of a weird subset of the plane with normal whatever. I guess the normal would be like 1, well, I guess -1, -1, 1 if we want the upward pointing normal. Anyway, I just follow the template that we've laid out over here, and I integrate ds, see here, works out to the square root of 3 because fx and fy are just both 1, so we get 1 plus 1 plus 1 is square root of 3. That's my ds. So this works out super nice. This works out super nice for a plane, is what's happening here. And then we just have to follow the integration through, and it's, yes, I could spend several hours of class working these things out slowly, but I think you guys, for the most part, understand the calculus here, right? So we're just trying to use the calculus we've already learned to do new problems. So next up, the flux integrals. I have a bank of examples here to look at with you. So here, we've got a sphere, calculating the flux of the vector field 1, 2, 3. But not through the whole sphere, just the part of the sphere above the xy plane, right? So if I could draw a picture. Bah! We're just talking about this part of the sphere, right? So we have 0 less than or equal to theta less than or equal to 2 pi. But what is phi range over here for the upper hemisphere? It's okay, I got it. 0 to pi over 2? I think that's right, right? Oops. And so, well, I guess you guys could look up there and cheat, right? 0 less than or equal to phi less than or equal to pi over 2. And that way I just select the upper half of the sphere, right? That was important. What would happen if we calculated the flux of this vector field through the whole sphere? What would happen? What would the answer be? I heard a 0. Why? This is a what? A constant vector field, right? So if you can imagine that, right? Whatever goes in one side of the sphere comes out the diametrically opposed side, right? What comes in goes out. There's no flux line that doesn't come in that doesn't go out, right? So yeah, the net flux most certainly would be 0, which tells me if I was to work this out over the lower hemisphere, I must get minus 12 pi. Yeah. And you probably could even see that in the mechanics of this calculation if you looked at it, right? Because instead of going from 0 to pi over 2, we'd go from pi over 2 to pi, which would flip this story around. So we worked this one. There's an error here, right? My typo. I meant to put n minus 1 all divided by 2 there. That's bogus, right? We talked about that already. This one here, I've actually talked to you guys about in example 5. This is example 5. It's the closed cylinder. Here I'm actually working out the integral of the vector field f equals 2. And I don't know. I need to fix this example so it's more interesting. It's like everything's 0 here, like x squared, z, and y. It just so it's kind of perverse. But here's the parameterizations on the the top cap. The wait a minute, what? That is, one of these is supposed to be 0. There's a typo here. What do I say? X1 is the, what's S1?
I think the second one gives it
The base is S2. So, oh, did I say 0 to, oh, but it's 0 to L, right? So this should be 0, because that's the base. That's supposed to be 0. That's a typo. Base, as you can see here, minus RZ hat. Notice that I flipped the theta and the R versus R and theta. That achieves my goal of flipping from Z hat to minus Z hat. See that's that trick in play there? But anyway, this one's not particularly interesting because they all work out to 0. I mean, non-trivially so, but they all work out to 0. This one I need to fix. We'll come back to this in a second. The last example here, I actually work out the integral of a vector field. So here's the vector field, minus x minus y e to the x squared plus y squared. And I'm doing it over the graph, which is the paraboloid, right? I think this is paraboloid, right? Circular paraboloid, I think. And the shadow of Bob is the unit disk here, right? Because like we're looking at the paraboloid that opens up, and it's from 0 out to radius 1 in terms of the domain. And so when I calculate the flux of this lovely vector field, I have to evaluating a vector field on the Monge patch is kind of easy, right? Because you just plug in x equals to x, y equals to y. But you just have to take the dot product with the PQR business. That works out to this here. And so I'm just find myself integrating. Well, I chose to change it to polar coordinates like that, right? And so there are problems where the spherical and the cylindrical frame are no help to us. This is such a problem, right? But all right. So my last example for today, I need to change that top example ever so slightly. So this here, I wanted to calculate the flux of the constant vector C, vector field C, over the portion of the plane, over the plane with vectors A and B. All right. But my parameters are not what I wanted here. So I'll fix it. Give me a second here. I got to find my notes. Oh man, where'd it go? Come on. Oh, there we go. So same problem, but we're going to do 1 less than or equal to, not 1, my bad. 1697 less than u squared plus v squared less than or equal to 42 squared. So basically you're on the plane and you've essentially got some kind of like a pineapple slice, but two-dimensional. Here's A, here's B, right? And we work out the integral. My vector field F is C. The integral over this, whatever you call this thing, S of C dot ds. For the reasons you guys can see up there, it works out to C dot A cross B, right? Times the integral over omega of du dv. But that's just an annulus, right? The region bounded by two circles. And what would that work out to here? We'd have C dot A cross B, right? Times pi, and then, well, this one was, 4 minus 1, right? Excuse me, what was it? Oh, 4 squared. Oh, I think that's a typo, actually. That should be, that's wrong. But this one I fixed. So 42 squared, because we do pi r out squared minus pi r in squared. So 42 squared minus the square root of 1690, square root of 60, well, just minus 1697. What do we get? What do we get here? Somebody work it out for me? What's this constant? 42 squared minus 1697. Anybody? Somebody knows it, but they won't say it. All right, very good. There you go. Seems like a fitting end.